In this video, we will talk about elementary reactions, which are the step-by-step processes that lead to our overall chemical reactions. Most chemical processes do not involve a single step. Instead, they are comprised of a series of steps. That series we call a mechanism. So the mechanism is comprised itself of a series of what we will call elementary reactions. The elementary reactions are the step-by-step process that make up our overall reaction. Now let's suppose we have a mechanism that for our balanced chemical equation is A plus B plus C goes to D plus E. Often whenever you have three things that are on the reactant side, these are rarely ever going to be one-step processes. Instead, they're comprised of many steps that when we add all those steps together, we get our overall chemical reaction. The reaction that make up the particular mechanism for this could be something like A plus P goes to D plus F. That F then breaks down to give H. The H reacts with a B and a C to give G. That G then breaks apart into E and P. Each one of these is called an elementary reaction. It is a single step process by which our overall reaction occurs. Now we have a term, molecularity, which describes how many different components are on the reactant side. So molecularity is the number of reactant molecules in an elementary reaction. In the case of the first step, A plus P goes to D plus F, the molecularity would be 2. There are 2 reactants for this process. The molecularity for the second step, F going to H, would be 1. There's only 1 reactant. For the third step, H plus B plus C goes to G, there are 3 reactants, so this is said to have a molecularity of 3. The last one, G breaks apart to E and P, would have a molecularity of 1. Now some of the components in our overall mechanism, we don't actually see them in our balanced chemical equation. The reason for that is some of these components are either unstable or short-lived. We call a lot of those components reactive intermediates. They are reactive, meaning that they are short-lived, and intermediates, meaning that they comprise steps in the middle of our mechanism. So an example of a reactive intermediate would be F. F is initially formed and then it gets used up in a subsequent step. So it is only around for the intermediate part of our overall reaction. D here, however, D is one of our products, so this would be a product. A shows up in our balanced chemical equation, so that would be a reactant. So in terms of our intermediates, F is an intermediate because it is first formed and then it goes away. H is an intermediate. It is formed and then goes away. And G is an intermediate. It gets formed and then goes away. Now there's another component in our balanced chemical equation here, and that is P, right? A reacts with P, so P is actually here and is not being formed. Instead, it's being consumed, and then we get it back. When you're looking at overall mechanisms, things that are first consumed and then produced are catalysts. Catalysts provide an alternate pathway for the reaction to occur. The key part for a catalyst is that we have to get it back in its original form at the end so that it can go back in sort of a circular fashion to react with another one of our reactants. So of the components, we have reactants, which you will see in your balanced chemical equation on the reactant side. You have products, which will show up on the product side. Then you have intermediates, which are first formed and then consumed. And then you have catalysts. Catalysts are first consumed and then reformed. So when you're all done, you get them back. Now, unlike our overall reactions, in which we cannot look at the balanced chemical equation and determine the rate law, for elementary reactions, we can. And the reason for the difference is for elementary reactions, these are single-step processes. So we know what components are coming together to make those individual reactions. For an overall balanced chemical equation, we cannot write our rate laws because we don't know what the sub-steps are. But for our elementary reactions, we know that it is A that is going to the products. It is not A reacting with something that we cannot see going to the products. So here, for things that have a molecularity of 1, those are called unimolecular reactions. Una for 1, unimolecular reactions. They, in our rate law, for the elementary step, it would be the rate is equal to K times A raised to the first power. So this 1 corresponds with the molecularity here of 1. For A plus A goes to products, this has a molecularity of 2. This would be called a bimolecular reaction, bi for 2, and it would have a corresponding rate law with a 2 here for the A. Similarly, A plus B gives rate is equal to K times A plus B. In each case, whatever the coefficient in front of our component in our elementary reaction, that is what the exponent is. Now, we could have a molecularity of 3, where maybe 3 A's or 2 A's and a B, or an A, B, and C come together. However, termolecular reactions, those that have a molecularity of 3, are very rare. And the reason that they're very rare is that having 3 components collide all at the exact same time in 3-dimensional space is highly unlikely, because it's highly unlikely for all 3 of those components to come together, collide at the same instant. They tend to have very low rates, and so they are rarely, if ever, observed. Each one of these elementary reactions, each step in the mechanism, can be thought of as its own reaction, with its own activation energy and its own rate law. The rate laws themselves for the overall reaction needs to be determined experimentally. However, the rate law for the elementary steps can be deduced from the equation in the step. And that's because when we know the individual steps, we can tell what things are colliding with each other, and from that we can tell how fast the process should occur. So in the case of step 1, the more hydrogen gas we have, the more times it's going to collide with the ICl, which would lead to faster and faster reactions. Now, the reason we can't do this for overall reactions, as we will see in subsequent videos, is that at times one or more of these reactions is going to be slower than the others, and that will throttle or slow down how fast the reaction can actually occur. These steps limit the rate at which the reaction can occur. The overall rate law itself needs to be expressed in terms of reactants and products. It cannot contain intermediates. The reason why we try to leave out the intermediates is because the intermediates are short-lived, which means we would not be able to add or remove these particular components to be able to speed up or slow down the overall reaction. Instead, if we can express the rate law in terms of reactants and products, then we can get a grasp of how to manipulate the reaction conditions in order for the reaction to speed up or slow down, whichever one we are after.